that I'm going to describe you. One is the first player are the car molecules, and you all know what car molecules are, and I will not go into it, but it's important to appreciate. Oh, it seems like something got stuck. Oh, no. So it's important to appreciate that in chemistry, car molecules were taken as a structural motif, and people didn't associate any special electronic properties to these chiral molecules. So even in biology, where we know that the most important molecules in biology, the proteins, all the amino acids, of course, DNA, sugars, and so on, they are all chiral. Still, people didn't relate any special properties to this chirality besides their structure. The second player in the game is the electron spin, and electron spin, it's well-established concept from the beginning of quantum mechanics almost, but usually we have two assumptions. First, that spin properties are important only if we have unpaired electrons. And the second is that the electrons, the electron spin, are very weakly coupled to the molecular frame. That's why we can do EPR spectrum, for example. So the molecule can rotate, but the spin maintains its own orientation in magnetic field. So spin was not viewed as a way to control chemistry besides photo dissociation, because the spin alignment doesn't define anything about the molecular frame. That was the main assumption. So what I'm going to show you, that in the cis effect, in the current-induced spin selectivity effect, both these assumptions are not the full story. And let's start very briefly. I'm not going through the theory, and I will avoid an equation here, but you realize that when electron has to go through chiral potential, and it's important for you to appreciate that chiral potential is always helical, even if the secondary structure of the molecule is not helical. Think about it as a asymmetric carbon. It has 4 different groups attached to it, and if you follow the electronegativity of this group, you get a helical shape of potential. So helical potential, electrostatic potential is associated always with chirality, and it means that the electron has to make turns while going through the molecule, which means that it has to share momentum with the environment. It has to share momentum with the molecule. And the electron can share momentum in 2 ways, either by giving a momentum or taking momentum from other electrons, but this means that the other electrons must be delocalized, because the localized electron to change their momentum requires a lot of energy, or it can do it by sharing momentum with low vibrational frequency, what we call chiral vibration, namely vibration that have angular momentum. And what is the evidence for this? So here's an example where we put molecules between, in a sandwich configuration, gold, we have chiral molecules, a layer of magnesium oxide to avoid pinholes, and then a nickel layer that can be magnetized either up or down. And by switch, we measure the current going through the system when the magnet is pointing one direction, the opposite direction, and as a result, we get the spin polarization, which is defined as the current going up minus the current going down over the sum of them. And what you see here, we measure it as function of temperature. And a big surprise for people working with spin is that when the temperature increases, the spin polarization increases. That's very unusual for condensed matter physicists. And here is the Arrhenius plot. And what you realize here that at 5 Kelvin, we get some spin polarization. It decreases when we warm up to 50 Kelvin, but at 50 Kelvin, something happens and we get a very strong increase in the spin polarization. So how we can understand it, and that's we did in collaboration with Jonas Fransson from Uppsala University. He derived a theory for it, and basically it comes because of the vibronic coupling of the electron with the low frequency chiral molecules. How low frequency? We speak here about 50 wave number, about. So it's really low vibrational frequencies. And as you see, the theory follows very nicely the experimental setup with very few assumptions. So we think we understand what's going on here. There is coupling of the electron with the low frequency vibration. But as usually in science, there are always surprises. So here it's another system. It's a molecule, chiral molecule, but that has no asymmetric carbon. This was done by a group of Zhang from Shanghai, and the experiment in my group was done by Yuta Zhang, a postdoc from Shanghai. And what you realize here, that there is no asymmetric carbon, but in the structure here, there are conjugated groups. Why it's important that they are conjugated? Because they, here in these parts of the molecule, there are electrons that are delocalized. And we use this magnetic contact AFM to measure the spin-dependent current. Basically, we put the molecule on the surface. We have a tip of an AFM here. We can magnetize the tip either with the magnetic field up or down, as you see here, and we measure the IV curve. And here you get it, and you see very clearly a big difference between the current when the tip is magnetized down, namely the north is pointing towards the molecule, versus the tip magnetized up. Another interesting finding here, that the current we get is huge. It's about 2 orders of magnitude larger than the current we get with regular molecules that have no conjugated systems. And here is the spin polarization. We get 75% spin polarization, room temperature. But what is really interesting now, that when we do the same experiment that I described before, but now we change the temperature, basically the spin polarization doesn't change much with temperature. So what's happening here? So what's happening here is that the electron that's passing through the system interact with these delocalized electrons and share with them the angular momentum. So it doesn't interact so strongly with the vibration, but instead it interacts with these delocalized electrons. And again, here the simulation from the theory, and we get nice reproducibility of the results with the same spin polarization. So what you realize, that electron going through chiral molecule must interact with the molecular system. So it couples the linear degree of linear momentum with the molecular system, and this is the essence of the Cis effect. As a result of it, the Cis effect is a room temperature effect. Not like the regular spintronics, where we prefer to work at low temperature in order to get good results. The Cis effect, because it involves vibrations and interactions that enhance the effective spin-orbit coupling, and I'm not going into the discussion here, but there are now theoretical papers by several groups, both in the US and in Europe, that calculated that this interaction is enhanced by temperature, and as a result, the effect is room temperature effect. It persists at room temperature. We don't have yet results at very high temperature to say what is the limit, I assume that some place it should start to decline. So that was one part. The second issue I want to discuss is the relation between the polarizability of the molecule and the spin. This work was done together with a group of Yossi Paltiel from the Hebrew University, and what I want to show here in a very briefly is the following system. We have here a whole device. In all device, current is flowing from source to drain. And typically in all device, we apply magnetic field perpendicular to the surface. As a result of a Lorentz force, there is a potential perpendicular to the current. That's called the Hall potential. In our case, what we do, we take the same Hall device, but we don't apply external magnetic field. Instead, we adsorb molecules here on the surface. Everything here is done in solution, and we have a gate. The gate is insulated from the solution, so we apply field on the gate, so it's electrochemical gate, if you wish, and we measure, we see if we get any Hall signal, and the first example is a case where we adsorbed on the surface DNA molecules. And here are DNA molecules that have damage in different position. These molecules we got from city growers from the US. And as you realize, when we apply the voltage, we get potential here. And actually, it's summarized, we think that potential depends on the voltage, but depends on the damage in the DNA. So why it's important? Because it tells us that the polarizability of the DNA and the spin polarizability depends on the damage. In the damage here, it's oxidative damage of the G base, and this damage not only affects the polarizability and spin polarization, but its position is also affect the polarizability. And that's really interesting because now we can come with a FM to which we attach oligopeptide here. And the idea is to measure the force between the oligopeptide that is modeling here, actually enzyme. So we have a alpha helix oligopeptides here, and we measure the force between this alpha helix and the DNA, the different DNA with the different damage. So you realize that if there is no damage, there is a very little force. However, the blue and red are the forces with the magnet pointing up or down respectively. So you realize that when we have damage, first of all, the force increases, but the force depends on the position of the damage. And that's maybe a hint how enzyme can recognize damage in DNA or find damage in DNA. That's a long distance recognition. So the enzyme it is attached to the DNA farther away from the damage, but because of the charge and spin polarization, the enzyme can feel that there is a damage and actually move towards this damage, guided by the force acting on it, on the DNA. So this was the issue of the polarizability, and now we go to real reaction. So only to summarize what I told you so far, I told you so far that the CIS is a room temperature. Another interesting thing is that when you apply field on a molecule, you charge polarize the molecule. As a result, there is a spin polarization, and the spin polarization can be detected as we did it, But it also means that when we apply voltage on chiral molecules, the singlet of the molecule, which is an entangled state, breaks. And we know which spin is at which end of the molecule. That's a very interesting observation that relate to much of the discussion existing today about qubits in molecules and so on. So now I move to another subject, which is real chemistry, or specifically oxygen redox reactions. And the one which is very famous is the water splitting. And I don't want to go into too many details into the molecule, but what is clearly here, that we have a strange situation. We start with water, which is singlet, and we end up with oxygen, which is triplet. So this reaction is principle is spin forbidden. So the question is how it occurs, and sure enough, when we do the artificial water splitting, people face two problems. One is overpotential, namely you have to apply potential higher than thermodynamic limit in order to make it to go. And secondly, there is the formation of hydrogen peroxide byproduct. Interestingly, in nature, this doesn't exist. So what is the difference? So our explanation is actually that in the process, one has to transfer 2 electrons each time. And if you have 2 electrons, you have the following situation. We have OH minus and OH minus. The OH is to give electron. If the spin of this electron is random, so there is a chance that one OH that is left with spin down, and that another OH is left with spin up after giving this spin. As a result, this is a singlet. So the product should be singlet, which is hydrogen peroxide, and we cannot form the oxygen. However, if we are able to control the system, then we have controlled the spin, then we can produce OH with the same spin. That's a triplet surface. Then we produce oxygen triplet, and we don't produce hydrogen peroxide. So how we do this? Simply we take, in this case, the catalyst iron oxide, and we coat it with chiral molecules. So you realize that we have achiral, that's the current versus voltage, achiral catalyst with no chiral molecules. This is the current when we coat the catalyst with chiral molecules, we get these results. Here's the hydrogen production itself, and you see it's a huge different hydrogen production with the chiral molecule. Now, what about hydrogen peroxide? So when we have no chiral electrodes, we produce, this is the signal of hydrogen peroxide observed by putting some dye that is sensitive to the hydrogen peroxide. So you see here we get a strong peak indicating that there is hydrogen peroxide. Now, when we use an electrode that's coated with a short chiral molecule, you see immediately the amount of hydrogen peroxide decline. And when we use longer chiral molecule, which is even better spin filter, then it decays even more. So basically what we have here, by controlling the spin, we can make a forbidden reaction to go. We reduce the overpotential and we avoid the unwanted byproduct. Basically, we make this process, the artificial process, more like the natural process that exists in nature. This can be done not only with chiral molecules, it can be done also with chiral inorganic electrodes, like oxide, different oxide, and the group of the Waldeck demonstrated some of this work. And now the last part of my talk will be real biology, or almost real biology, and that was done together with my colleague Gilad Aran. So the idea is the following. We take antibody, we touch the antibody with a linker to ferromagnetic surface. And now there is an antigen in the solution with a dye. And we monitor the association of the antigen with the antibody by monitoring the fluorescence from the antibody with a confocal microscope. So that's basically the experiment. And you see immediately here that for one direction of the magnet and the other, there is different rate. So this rate of the reaction depends on the direction of the magnet here. And the way to understand it is quite simple. When the antigen is approaching the antibody, it induces charge polarization in the antibody because the binding here is an electrostatic binding. This charge association means the charge has to move towards this position. If charge can move also from the substrate, then the effective polarizability of the protein increases, and then we have stronger binding. If we block it by flipping the magnet here, so electron cannot penetrate in, then the binding is slower. So that's simply the effect, but we can do it in a even more sort of clean way. And now we touch the molecule to any substrate, not magnetic, not conducting, doesn't matter, but we place a dye in different position in the protein. And now we excite the dye with circular polarized light and monitor again the binding of this group that has a dye on it to the protein here. And what we see here, that with light, we get faster rate than with no light. But interestingly, in here, please look here, only the left-handed circular polarized light, namely counterclockwise circular polarized light, only this polarization is effective. The right-handed, basically it's the same like no light. So there is a clear indication when we excite the dye with circular polarized light, then it's known that we excite specific spin because of the spin-orbit coupling in this dye. That's a known fact. And as a result, only this spin can move inside the protein and affect the reaction. It cannot be done with the opposite spin. And not only it can affect the interaction, it can affect also enzymatic activity. So you see here the enzymatic activity with no light, and if we put left circular polarized light, we get reduced in the enzymatic activity. The right is basically very much like the no light. So again, one specific spin plays the role here. It's important to appreciate that the effect depends not only on the light, but also on the position where we put the dye, and we see different effects for different positions, and that's actually gives us a way to map the way information can be transferred in the protein, and to learn how this connectivity of polarizability in the protein affects its reactivity. So clearly we have here an example of affecting by spin reactivity of proteins. So to summarize, chiral molecules, as I mentioned, were important mainly for their structural role. However, when we have the cis, it can be important in many other applications. Spintronics, I didn't go into it in detail, spin selective chemistry. I showed small example, but there are many more examples now. We can control multiple electron reactions, like I described in the case of water splitting. We can use it for enantiomer separation. We use magnetic surfaces to separate enantiomers, and we can understand better enantiomer specific interaction, because as we demonstrated, interaction between chiral molecules is not only depends not only on the shape, but also on the spin interaction due to the spin exchange. And that's another subject by itself that we study. So here are the people that do the work. Those with the circle around them are my present group member. And as you know, usually they are the ones that do the work, and I'm going around and speak about it. And thank you very much.
Great. Thank you very much, Professor Neiman. Very interesting talk. Do folks have questions? We have a little bit of time. And you can use the hand raise item if you'd like, or also, if you notice a lull.
Elena,
Yeah. Yeah, please go ahead.
Actually, I have two questions. First is chiral selectivity is not 100%, right? And I would like to know, just to hear from you, what's the reason for that, or what you think could be a mechanism? Is it's not 100%
for enantiomer selectivity?
Yes, for chiral selectivity, it's actually not chiral transfer is not 100%, but less. What's the reason for that? And second question, I'm asking pretty much all professors who teach biochemistry. What do you think? What's your explanation why majority of molecules, biological molecules, are L and not D?
Okay, so I will answer your second question first, because it's easy. I don't know why they are L and not D. But I know that once chirality was defined in nature, in evolution, it has to be the same chirality. So why it's homochiral, I have explanation. Why it's L and not D, I think it's arbitrary, if you ask me. It happens, and they are studying this effect. There are several groups that study this effect, but I don't believe that there is something special in being a amino acid L and not D. Actually, you can make proteins that are D and they function the same way. So that's, I don't think there's an answer. Now, regarding the enantiomer selectivity, it's a really interesting issue. First of all, in recognition, and that's important, in nature, the enantiomer selectivity is fantastic. It's really unbelievable. If you try to buy a oligopeptide, if it's taken from L amino acids, you get very pure system, 100% pure, but artificially you can't get 100% pure D amino acid. So nature does it in an amazing efficiency. And the question how? And we think we have the answer. As I said, when two molecules are approaching each other, they apply field on each other. By definition, there is special forces, and therefore there is a charge polarization that is accompanied by spin polarization. It's a transit spin polarization. But now, and we publish a paper about it, PNAS, so you're welcome to look at this. Now the interaction is not simply the special interaction, but there is a spin exchange interaction. Spin exchange interaction, to give you a feeling, is on the order of singlet triplet splitting. So it's a huge effect. It's a very, actually we measure it, it's on the order of 100 milli-electron volt. So many times KT. As a result, that helps in the recognition. However, it helps only at short distances, because the spin exchange is a short range interaction. Biology happens always in a crowded environment. So in crowded environment, of course, the speed exchange is very important. So I think that's the secret of chiral selectivity in nature.
Thank you so much.
Okay, great. Thank you very much, Professor Neiman. That was almost a little bit of additional seminar, so much appreciated. So, so just to stay on time, we're going to move on to Professor Bonsanti. Thank you very much for connecting. She's out in Switzerland, so also getting to be evening. So thank you for letting us intrude on your evening a little bit. And she's going to be talking to us about colloidal nanocrystals to advance catalysis and energy technology. So I think, I'm not sure if, Rafael, are you able to just...
But Ron has to stop sharing. Perfect. That's great.
Okay.
All right. All right, so yes, here we change. Thanks a lot, Richard, for the invitation and the opportunity to share with you some of the science that we have been doing in my group in the recent years. And we change completely topics. And indeed, we talk about catalysis and some photochemistry as well, photophysics as well. But I come mostly from a background of materials chemistry. And I start by motivating my presentation with the fact that sustainable and that affordable clean energy and climate action are among the 17 sustainable and development goals set by the United Nations to reach by 2030. And to reach these goals, we need advances in many sustainable technologies critically depend on our ability to design, realize, and tune nanomaterials with optimal properties. And having to deal with the nanomaterials with high surface-to-volume ratio, the interfaces, which include exposed facet, defects, surface passivation, surface functionalization, play a key role, actually, in advancing these sustainable technologies. So this connects actually well to the topic of this symposium. And if we think about tunable materials, actually colloidal nanocrystals fulfill these criteria, and they have enabled indeed the discovery of different new phenomena, as well as provided technological solutions. These colloidal nanocrystals, for those in the audience that are not familiar with them, and I introduce them, so this will facilitate probably also the speakers in some of the next presentations. They are constituted by an inorganic core and a shell of ligands. And the most known are quantum dots, and when we change the sides, we change the optical properties. And quantum dots have been successfully integrated into displays. We have also noble metals, and here I'm showcasing gold, which has a pink color because of the presence of surface plasmon resonance absorption. And these particles are integrated in different sensing devices. And I'm not mentioning those colloidal nanocrystals of different compositions which have enabled unique applications in different fields. And what my group specifically does is that we try to understand the chemistry behind the formation of these nanocrystals and their interfaces so that we can control their function and eventually contribute to address challenges in catalysis and energy research. And today I will share with you some of the results in two different topics. One is electrocatalysis, where the interfaces involved are basically the facets between the atomic arrangement on the surface of these nanocrystals and the environment. And some of the results that we have been having with this new methodology that is the colloidal atomic layer deposition. So let's start with the catalysis. Well, the motivation here is to take electricity and the CO2 and water and being able to make many of the chemicals which nowadays are extracted from petroleum, and that they are crucial to make medicine, material, fuel, agrochemicals. And to do so, we need a catalyst which selectively breaks bond of CO2 and water and forms new bond. Now, it turns out that copper, for reasons that I don't have the time to explain here, is quite unique in this sense. However, if you take a bulk copper foil, so with poorly defined surfaces, this copper is going to generate 16 different products, which will be a separation nightmare for chemical engineers. Now, there were studies on single crystals of copper reporting that certain facets of copper can become more selective towards certain products, such as methane or methane in the case of the 111, or ethylene in the case of the 100. So the first question to ask is if we could make shape-controlled copper nanocrystals so that we could look into these properties, but under more realistic conditions compared to the experiments that are done in single crystals. So actually what we did to develop the synthesis of copper and was to really understand the chemistry behind the formation of copper nanoparticles. So this is a typical three-neck flask that we use for the synthesis of nanocrystals. We brought it to the synchrotron to perform in situ X-ray absorption. And thanks to this measurement, we could identify the chemistry, some of the chemistry involved. And thanks to this, we have been able in the group to synthesize quite a library of copper nanocrystals. And here I'm showcasing simple copper spheres where we change the sides, cubes when we change the sides, and octahedra where we change the sides. With these well-controlled copper nanocrystals, we could demonstrate that indeed this is the Faraday's efficiency, which indicates the number of electrons converted into product versus the applied potential to the device. And we could demonstrate indeed that the cubes exposed in mostly 100 facets are mostly selective for ethylene, and that the octahedra are mostly selective for methane, which are results consistent with the single crystals, and that the spheres exposing different facets on their surface are actually not selective for any specific product. However, we also understood something more. Indeed, based on the single crystal studies, we would have expected that the bigger cubes showed the highest selectivity for ethylene. However, this is not what we found, because we found that the intermediate size of the cubes was actually the most selective for ethylene. And we explained this by theory which proposed the edges as indeed the location where the CC coupling needed for the ethylene formation of cubes. So basically this copper, this interface between the copper, these well-controlled copper nanocrystals allowed us not only to confirm some of the selectivity trends observed in single crystals, but actually to go beyond them, because we could identify an optimal size, which implicates the importance of edge size. Now, copper is quite unique. However, it also suffers from some limitation, and there is a lot of interest in the field in looking for bimetallic structures. And to improve further the capacity of copper to form CC bonds, one of the conventional combination is to have copper coupled with a CO generating domain. In this case, we started to combine copper nanocrystals with silver in what is referred to as a tandem scheme. In this tandem scheme, we have that silver generates CO, and then the CO is converted to ethylene. And what we did here was a simple physical mixture where indeed, because of this tandem effect, we could observe an increase in CC coupling when we mix the two particles. However, then we also started to create what we refer to as heterodimers, where this copper and silver share an actual interface. So they're epitaxially grown into each other. And what we found is that this interface between the two domains further enhances the CC coupling capabilities. What we demonstrated by combining UVVs and XPS measurement is that a charge transfer occurs between the copper and the silver, which leaves behind a slightly positively charged copper, which can modulate the CO binding energy. And therefore, here the presence of this interface becomes actually crucial to enhance the CC coupling along, so this electronic effect arising at the interface because of the charge transfer are crucial to enhance CC coupling along with the tandem effect. I also want to point out that also in this case, the facet that is exposed matters tremendously, because as we start to combine in a similar fashion copper cubes and copper octahedra, instead of spheres, what we observe is that in both cases, there is an enhancement of the Faradaic efficiency for ethylene, which is expected based on the tandem catalysis. However, there is even it was a surprising result to find that actually the copper octahedra selectively prefer ethanol over ethylene, which provided then insight into the mechanism behind ethanol formation, which I won't go into the details of. Because I also want to propose always, I also want to refer to the importance of the interface, not only when coupling this copper with another metallic domain, in the case I mentioned was silver, also, for example, if we start coupling copper with the molecular catalyst. So actually, still we can also start picking molecular catalysts, which are CO producer, instead of metals. And what is the advantage of molecular catalyst is actually that we can change their production rate for CO and the voltage at which the CO is generated, depending on the ligands that we have around the active center. And then because both the molecular catalyst and our nanocatalyst are soluble in solution, we can really start to mix them and to find the conditions and the loading and the matching of the production of CO and all the voltage that actually enhance the CC coupling also in this case. And what was interesting here to discover, also in this case, is that we actually need the molecular catalyst to be in contact with the copper in order to generate this CC coupling, and not simply in the vicinity of the copper. And this indicates that, again, the presence of synergistic interaction and of direct transfer of the CO from the molecular catalyst to the copper cubes, rather than diffusion of the CO in the electrolyte. So again, the importance of a actual interface between the two components. And we will continue now our journey into interfaces by looking more at the surface chemistry of nanocrystals with this colloidal atomic layer deposition. So I mentioned in my first slide, or in one of my initial slides, the importance of quantum dots for displays. Of course, okay, there are many different applications. For sure, there is photovoltaic, biological applications, cameras, displays, LED, and various ones. And ligands, generally, they play a key role, both during the synthesis, but also in conferring, eventually, the colloidal stability to the particles. Now, these ligands are in a dynamic equilibrium with the surface, which is also what allows the nanocrystals the colloidal nanocrystals to grow during the synthesis. Now, one issue is that this dynamic equilibrium eventually because of this dynamic equilibrium, eventually the quantum dots and the colloidal nanocrystals can lose their colloidal stability over time, especially if we are in very diluted or concentrated solution. And also another issue is that many of the quantum dots are actually sensitive to oxidation or sensitive to being handled under ambient environment conditions. So we thought if we could actually build a thin shell around these nanocrystals. And we wanted to build a thin shell of oxides similar to what happens in atomic layer deposition. Now, if we want to build this thin layer of oxide, in the past, there are silica coatings that have also been widely used for biological application. But these silica coating generally are synthesized by the stopper of microemulsion methods that require water and often acid and base catalyzed, and this is not compatible with the sensitive cores. Also, we have quite thick shells, so they don't work if, for example, we would still like to have some charge transfer happening, and it's difficult to fine-tune the shell. On the other side, we have a gas phase ALD, which is great to tune the thickness of oxide coatings. However, it's in gas phase, so it would be nice to keep our colloidal hints. So what we introduced is this colloidal ALD, which simulates the gas phase ALD, but occurs in solution and at room temperature. Is based on the sequential injection of a reactive precursor for the oxide and oxygen. Furthermore, we also add ligands during the growth. So I like to highlight that these shells, in the end, they are amorphous, hybrid, oxide, organic compounds. And they possess, as I will show you, quite unique properties. Now, the first work on this colloidal ALD was simply to report that we could grow this shell around a large variety of cores. Oxide, some perovskite, and that by changing the number of cycles, we could change the radius, the thickness, and that the shell thickness changes depending on the number of cycles. Now, we also started to learn a bit more about how this TMA reacts on the surface. And what we discover is that we require an oxygen site. So basically here, the oxygen site can be the ligand themselves. So if we have, for example, something like oleic acid, the shell of alumina grows around the particles. Actually, you don't see here the shell because it's amorphous and because there's a low contrast in the microscope. So we verify that it's here by different means. Then if we don't have, we can also have an oxidized surface, and also in this case, the shell grows. If we don't have any oxygen on the surface of in the ligand, it's clear at this point that the aluminum oxide nucleates separately. We also understood a bit more about the interaction of the oleate ligands and the TMA by performing solid-state NMR, which told us that indeed the ligands can act as, sorry, I'm not sure what happened, can act as nucleation sites. Then, okay, we go back to our original question, if this thin oxide shell could actually lock the ligands in place. And we took as example two different case studies, which are lead sulfide and perovskite, which are two types of quantum dots, which are largely used in PVs. And normally, these quantum dots, for example, lead sulfide, they have oleic acid on the surface. And when you start to make device, you exchange your oleic acid with dithiol because you want shorter ligands. And you can monitor, and your solution crashes here. And you can monitor the substitution of the oleic acid with the dithiol by NMR. Now, it was clear as we did this test in the presence of the tin oxide shell, that the exchange does not happen and the solution remains stable. And we were also basically able to demonstrate that we can make really highly concentrated inks, and these inks remain stable, and that allow us to obtain very thick films, which are 500 nanometer, in one deposition. While normally you need to multi-layer diluted concentration to get to this point. More recently, we also demonstrated that as we start growing this amorphous zinc oxide shell around indium phosphide, we can also increase the photoluminescence quantum yield of the compared to the as-synthesized quantum dots, which we explained via some defect passivation of on the surface of the DMZ, which is the precursor of the zinc oxide shell, of some defect passivation on the indium phosphide, as well as some interfacial some interfacial oxidation developing between the indium and the zinc oxide shell. And furthermore, okay, the advantage of this shell is that we can lock again the ligand in place, and as we lock the ligand in place, we also confer colloidal stability under ambient environment to the indium phosphide, which can then remain for months stable in solution when exposed to air. Another application that we demonstrated of this shell is actually related to create these multifunctional materials, where what we did was to add in the shell functional ligands, where these ligands are actually allow transfer from and energy funneling from the core eventually to the outside of the shell. And I was faster than expected. I guess this is the Zoom effect. So I wanted just to give you an idea of how understanding the chemistry of nanocrystals and also of the interface, how interfacing these nanocrystals with different materials can allow us to solve challenges in catalysis. So I show you how the form of and the shape of these copper particles determines their selectivity for CO2 reduction. So for example, these copper cubes of certain sizes becoming highly active for ethylene, or also when we create interfaces of copper octahedra with silver, they can become selective for ethanol. We can also specifically interface these particles with molecular catalyst, and I didn't go in much details about the mechanism because I wanted to keep a bit light the talk. And I also showcases a few examples of this new methodology, which is the colloidal atomic layer deposition, to create these organic inorganic hybrid materials, which allow now to combine different cores with ligands and with oxides all together. And generally that, yeah, we need to develop the chemistry of well-defined and tunable materials with controlled interfaces if we want to advance sustainable technologies. And with this, I like to thank the wonderful group of people that I have the pleasure to work with, fundings, also facilities, because we use quite a bit of synchrotron facilities, and you for your attention.
Great, thank you very much, Professor Bonsanti. So wonderful talk. Do we have questions from the audience? And maybe I'll start out with one. When you started working with copper particles and things like porphyrins, I think as you call them a co-sensitizer, were there other chromophores that you tried to look at, or which properties were you most interested in with regard to using molecular species, because the copper also has things like large absorption cross-section. So is it the lifetime or the extinction coefficient, or?
Yeah, no, so it's interesting. The thing is that here we were not using these as photocatalysts. So it's all electro, because the porphyrin are excellent electrocatalysts to generate CO. And so we have never looked at this system with the idea in mind of any like coupling photo, like here they're not used as sensitizers, they're used as electrocatalysts to generate CO. So it's only the potential that we are applying. But it can be a good idea also to start using them as photosensitizers, actually. We have not done that.
My brain just jumps to photochemistry. So because the systems, that could be interesting in terms of recruiting photons and being able to drive this where it's a complete cycle in one system. So people look at this for homogeneous catalysis, or it's kind of quasi-homogeneous because there are solid surfaces, but it's it's all turnovers in one system.
Yeah, I guess they could. I don't know. Yeah, I'm not sure in terms of light, because then we would rely on copper for like some sort of plasmonic catalysis, or yeah, I don't know if the two systems will work well together in that sense.
Okay, I see. Thank you very much. I see a question from Tim Lane.
Yeah. So yeah, this is a good slide here. So you mentioned here that you see this enhanced effect when the molecule or when the molecular catalyst is interacting with a copper. Is that correct? And
Yeah.
I think you attribute it mostly to the sort of proximity effect, where they can do essentially work as a sort of cascade catalyst.
Yeah,
right?
right.
Yeah. And I was wondering, do you know the extent of interaction between a molecular catalyst with the metal? Are they physically in contact? And
yes. I don't know if I have slides. No, I don't have slides, but this is exactly what. Yeah, we did some. So in this work, basically, we explored. We started to see if there is some electronic interaction, basically, between the molecular catalyst and the copper.
Mhm.
And we didn't see big changes in XPS, but we look only at XPS, basically. We didn't look really into the details. So the way in which we did this experiment is by, in one case, to really deposit the molecular catalyst along with the copper, and you really could see in the TM that the cobalt and the copper are colocalized if you do EDX mapping. And then in the other example, we mixed first the molecular catalyst with the carbon, and then this one was mixed with the copper cubes, and you could clearly see the two metals, so the cobalt and the copper, separated in the EDX mapping. But then really the nature of this interface here, I don't know yet.
Yeah. So if this catalyst lights flat, for example, on a copper surface, you could imagine a pretty strong electronic interaction.
Yeah,
That
totally.
could change the charge density on the cobalt and things like that.
Yes. We didn't go in. Yeah, this was just a first proof of concept. But of course, it would be nice also to start studying the assembly almost of these, and by loading, changing, for example, the different loading, and trying to look a bit more carefully into this type of interaction. Also, the NMR could help us maybe to determine the arrangement of the molecule. I think, or also, for example, to see if they arrange differently on the 111 surface or on the 100. So there can be more. More experiments to do, actually.
Yeah. In fact, you could probably do a Raman measurement. This molecule probably will be enhanced on copper surface.
Yeah, that's also a good idea.
Okay. Do we have other questions? Maybe one other just quick question for me with the last part of your talk with the functionalization with other molecular species. are you starting to think of certain targets of what you aim to achieve there? With some of those organics, they have low-lying triplets, for instance, so you can get kind of I don't know if you'd say unexpected, but electronic interactions that can be it depends quite a lot on what the exact electronic density states is for those species.
Yeah, so this was indeed the triplet energy transfer. So they were picked in order to favor the triplet energy transfer. And the thing, I mean, the nice thing is that now, I mean, we demonstrated the possibility of obtaining this multi-excitonic structure. And so you can start loading the shell many different type of molecules. So this was just a proof of concept here.
Okay, great. All right. Well, thank you very much for the presentation.
Thank you.
Great. So, so our next presenter is Professor Aaron Lindenberg from SLAC Stanford, and he'll be talking to us about ultrafast probes of interfacial charge and lattice dynamics. And he, interestingly, is actually at Argonne, but not for purposes of necessarily this workshop, due to additional meetings.
That's right. Yeah. Thank you very much, Rich and Elena, for organizing this. Yeah, weirdly enough, I am at Argonne here for another meeting. I'm giving this talk from the guest house. So it's kind of a sad feeling that we're doing this over Zoom and not in person. But anyways, I want to talk today about some ultrafast experiments focused. Really, the entire talk will be focused on van der Waals materials, 2D materials, which are essentially, you know, as you all know, essentially all interfaces, and many of their emergent properties emerge and arise from interlayer, interfacial kinds of interactions. So I'll talk about new ways of probing the kind of coupled charge and lattice and phonon dynamics that underlie these properties. Let me just start with the acknowledgements. Actually, many people contributed to this. I don't even have them all listed here. The first part of the talk, which will really be an introduction, will be about kind of applications of terahertz spectroscopy, terahertz emission spectroscopy to probe charge transfer. And these were experiments led by Barak Gazulturk, who's actually now at Argonne here at the Advanced Photon Source. And then the second part, the real meat of the talk, was work led by Aditya Sood in collaboration with many others. That's the SLAC UED source at Berkeley, significant theory contributions from Felipe Jornada, work co-led by Archana Raja at Lawrence Berkeley National Lab. All right. So here's the brief outline, kind of a warm-up. I'll talk about some now published work using terahertz emission spectroscopy as a way of directly probing the currents, the electronic currents that are associated with charge transfer processes in a van der Waals heterojunction. And then the second part, as I mentioned, we'll talk about experiments using ultrafast electron diffraction, where we really try to probe the phonon mediation processes that enable these charge transfer processes. And then I'll have a couple of brief comments on kind of future directions and things like that. Okay, so I probably don't have to mention to all of you, all of you are coming from different fields, but interested in interfaces and in some sense, and of course, dynamics at these interfaces plays a central role in a really broad range of material systems, really underlies the functionality of these systems. As I mentioned, this talk will all be about these van der Waals materials, these materials where you can essentially stack these kind of two-dimensional layers on top of each other. Again, as probably many of you know, the interlayer coupling, the interfacial coupling between these layers really underlies a vast array of kind of amazing emergent properties. All of the complicated correlated phenomena that arises from these materials, ferroelectricity, and so on, is in many ways mediated by these kind of interlayer couplings. So it's an important goal to try to understand these processes and the dynamics on which these processes really occur. All right, so what are some arguments for why you'd want to kind of think about these types of electronic and lattice interfacial dynamics? So I already mentioned one example, ultrafast kind of charge transfer. What I have here on the left, this is kind of a prototypical example of a type 2 heterojunction. This kind of process underlies optoelectronic devices, photodetectors, and so on. And in this kind of type 2 junction, if you excite electron hole pairs across the gap, essentially the lowest energy state for, in this case, the electrons lies on one side of the junction. The lowest energy state for the holes lies on the other. So you form this kind of interlayer exciton, which is, again, a topic of important interest and many kind of interesting properties arising from these things. And so there's been a long-standing question, and I'll talk a little bit more about this in just a second. There's been a long-standing mystery, really. Why is the charge transfer processes in these materials so fast? In a kind of a very naive picture, you might imagine the weak van der Waals bond essentially, gives rise to very weak interlayer coupling, and maybe might enable very, very slow charge transfer processes. It's exactly the opposite, as I'll show you. So what are the mechanisms underlying this? And there's been much theory and a lot of discussion about the ways in which phonons can assist this type of charge transfer processes. So this is kind of one argument for why you don't want to just probe the charges. You need to also probe what the atoms are doing and things like that. And then a second argument is kind of underlies this question of, well, what are the phononic mechanisms that couple, for example, heat across these layers? This is a question that is of great importance for devices, for cooling. If you have a transistor, a two-dimensional transistor-like device, thinking about energy dissipation and the ways in which energy is coupled across these weak van der Waals junctions is a central question. And I'll talk about in this talk how we can really directly measure this effective resistance that defines the kind of coupling of phonons across these atomic junctions. And then a second kind of argument for why, lattice response and the motion of atoms is really important. In these van der Waals systems, it's very common, to kind of think of these individual layers as kind of rigid blocks kind of sliding past each other, maybe. So, of course, the weak van der Waals bond enables sliding kinds of excitations. But, within each two-dimensional layer, the picture is these things are covalently bonded and quite rigid. But it's also really quite well known now that even that picture breaks down in these systems, that there are kind of significant reconstructions within the two-dimensional layers of these structures. I'm showing on the bottom here theoretical calculations from Tim Kaksiris's group at Harvard, kind of just showing the kind of displacement fields, the variation in the band structure that occurs when you create an MOS2 WS2 junction. So these things are, by no means rigid blocks. They're heterogeneous. This, is all connected with the moire properties of these materials. Okay, so I mentioned briefly already that, even dating back to kind of 2014, almost 10 years ago, it was known that the charge transfer processes in these materials is very fast. This was kind of original work from Feng Wang's group at UC Berkeley, and this is a great review paper which kind of summarizes the kind of state of the field on this. Here's the data. These are kind of tabletop transient absorption and transient reflectivity measurements. Essentially, you excite one of these heterojunctions, and what you're doing in kind of a rough sense is you're probing the kind of band filling. So you're looking at the population when charges cross the interface, they fill particular electronic states, and this modulates the optical properties, the absorption, the reflectivity. And so the key kind of experimental observation here was that this process is occurring essentially on time resolution limited kinds of dynamics. They're not even resolving it. They didn't have the time resolution to resolve this process. So, and then follow-up measurements have really shown that this process is really occurring much faster than, kind of 500 femtoseconds on kind of 100 femtosecond timescales and below. So what's the mechanism for this? Where is the energy dissipated? What is the role that phonons actually play in defining this process? Okay, so let me talk about, let me get to sort of the first example of some real experimental probes of this. So one of the challenges, I would say, of the transient absorption spectroscopy and reflectivity is that what you're essentially doing is you're probing the kind of band structure of the initial and the final state. It requires detailed materials knowledge. There's a number of different processes that can modulate the optical properties of these materials. It's very difficult to quantify, for example, the efficiency of the charge transfer through these types of approaches. And so we started thinking about kind of more direct probes. And so the first example I'll just very briefly mention are experiments where instead of trying to kind of probe the band structure, what we do is we really try to zoom in and really watch the motion of the charges themselves across the interface. And of course, when this kind of interlayer exciton is formed, when charges jump across the interface, this is a time-dependent current. And we all know, if you're at Argonne, then this is the principle that underlies how a synchrotron works. We all know directly from Maxwell's equations that when you have an accelerated charge, the kind of ordinary kind of radial Coulomb fields falling off as 1 over r squared gets turned into kind of a 1 over r like scaling, gives rise to a radiated electromagnetic field. And if the dynamics of this process, of this kind of charge transfer process, are happening on picosecond or sub-picosecond timescales, and this is going to give rise to radiation at the inverse of that, at a frequency corresponding to terahertz frequencies. Okay, so this idea is again not a new one. There have been many examples of this, even dating back to 1990. I think this might be one of the first examples, probing kind of band bending at an interface under photoexcitation. Charges move in this kind of interfacial field and give rise to a kind of a single cycle electromagnetic field pulse. The Fourier transform of this pulse as a function of time, the Fourier transform gives you a kind of a frequency spectrum, which is, peaked at, frequencies of order 1 terahertz, something like that. Another example, these are kind of pioneering experiments from Matt Beard's group in various chemical systems, probing charge transfer processes within molecular systems in solution and things like that. Okay, so we've been thinking about this for a while. We've applied this approach, for example, to examples in the hybrid perovskites, where you can actually see, separate from the charge motion, you can actually see indications of kind of lattice modes and really get information directly about electron photon coupling. I won't talk about that here. And we said, all right, well, do we have enough signal to noise essentially to really probe the current from a bilayer, probe this transient current at angstrom length scales at femtosecond time resolution. So the experiment is pretty simple. We come in with a 400 nanometer pulse. This is a WS2, MOS2 heterojunction, and we record using electro-optic sampling the radiated kind of terahertz field coming from the sample. And so here are kind of some simple kind of experimental results, which kind of show what we actually measure. So the first thing you can do as kind of a control is you can just measure a signal from a pure monolayer, so a pure MOS2, for example, or a pure WS2. And so if you do that, then essentially you measure nothing. So, in this case, there are some very weak signals, even for the monolayers, I would say. But to first order, the response is essentially negligible for the monolayer. However, when you form a heterojunction now, when you form a bilayer, so this is now MOS2 on WS2, now you get a very clear time-dependent signal. Again, the spectrum here, the time-dependent electric field that we measure is directly related to the time-dependent current flowing across the material. And then interestingly enough, if you change the stacking order, so you essentially flip the order at which the heterojunction is deposited, this of course changes the direction of the time-dependent current. This current flips from pointing out of the film to pointing into the film, and this changes the polarity of the emitted terahertz field. So by measuring the polarization state, you can directly extract information not just about the magnitude of the current, but also the direction in which the charges, the electrons and the holes are actually flowing. I don't have time to really talk in detail about all of the results of this measurement, but I will just say that through some more detailed fitting, one can really kind of try to extract mechanistically information about these currents. You can try to separate out the timescales for kind of relaxation processes of excitation of hot carriers to the bottom of the band from a kind of an interlayer charge transfer time. You can extract quantitative information on these magnitudes on the efficiency. We extract direct quantitative measurements on the efficiency of this process. And then we also saw, interestingly enough, the kind of emergence of this kind of saturated behavior, which we can relate to the kind of buildup of electric fields across the interfaces as this charge transfer process occurs. Okay, and there are ongoing measurements now, which I won't talk about, essentially doing these measurements, but measuring these things as a function of the twist angle of these heterostructures. Okay, so let me now jump to the second part of the talk and talk about experiments now using femtosecond electron bunches. These experiments done at the MEV UED setup at SLAC. So now we have the same type of heterojunction. This particular sample is a WSE2, WS2 bilayer. It's actually encapsulated inside hexagonal boron nitride, and then it's kind of freely suspended on a support structure. So we can do transmission mode electron diffraction experiments, probing the structure, and under kind of optical excitation. So here's kind of on the right here, this is a measurement of the diffraction pattern. It's a really kind of amazing diffraction pattern, I think. Every spot here is a diffraction spot, but what we're measuring here in this transmission mode is the superposition of the diffraction patterns from all of the layers in these samples, from the single WSE2 layer, from the WS2, from the hexagonal boron nitride. We can identify each one of these. And now if you zoom in on kind of one of these Bragg peaks, the power of this approach is that it allows you to really separate out the contributions from each layer. We're not, as in a typical optical experiment, averaging over the whole structure. We can really say, I want to measure the temperature, the local time-dependent temperature in one of the layers as a function of time, compare that to one of the others, and so on. So how do we actually interpret these experiments? Essentially, what we're going to be doing is kind of the simplest possible kind of thing. We're going to be looking at the intensities of these particular Bragg peaks. And I won't go into a kind of a detailed explanation of this, but I think all of you maybe know that, in any solid, if the atoms are jiggling around more as the temperature heats up, this is going to reduce the intensity of the Bragg peaks just from the increased disorder in the sample. This is essentially known as a Debye-Waller effect, and essentially this kind of simple model relates the intensity of the Bragg peaks to the mean square displacements of the atoms, which in turn are related to the temperature of the structure. So through this type of analysis, we're able to make plots of the time-dependent temperature in each of these systems. Okay, so I'm going to show you kind of two different experiments where we kind of probe interfacial coupling in these systems. The first is a measurement where we actually add an additional layer. So we have an additional thin aluminum layer on top of this heterostructure sample. So now the idea is we come in with an 800 nanometer pulse. All of the energy is just directly absorbed in this top thin metallic layer. And now what we're essentially probing is the kind of baseline phonon mediated transport. This is like heat conduction, directly trying to probe the effective thermal resistance across these different structures. Of course, there are many interfaces in these samples. So you're really probing, transfer of energy from the aluminum into the HBN, from the HBN into the 2D heterostructure, and so on. So here are the kind of experimental results, plotting the change in the temperature of each of these two layers. So we're zooming in on first the Bragg peaks associated with the WSE2, then with the WS2, and we can independently plot the layer-specific temperature in this response. And so what you see are kind of a couple of things. First of all, the response is quite slow. The axis here is in kind of hundreds of picoseconds. So you can see that both layers start to increase right around time zero, right when the optical excitation pulse in energy is initially absorbed into the top metallic layer. And then they increase on sort of a few hundred picosecond timescales. And then at long timescales, even out to kind of 800 picoseconds, you can see that the WSE2 layer in red and the WS2 in blue are actually still at different temperatures So the thermal conduction, the thermal equilibration that is, of course, occurring has not yet completed. And in fact, you can kind of compare this to kind of first principle simulations, solving essentially, I shouldn't call them first principles, essentially solving the heat diffusion equation across these kinds of layers. And you can show that in fact, this equilibration process, is really not actually occurring until timescales of order many tens of nanoseconds, longer than we can actually probe in these experiments. Okay, so from these types of measurements and from a detailed kind of heat diffusion model, we can essentially the key input in this key input into the equation is this kind of difference in the temperature between the two layers. We can extract directly information about the kind of this effective resistance. This is oftentimes encoded as this is sometimes called the Kapitsa resistance. The inverse of this is called the thermal boundary conductance. And we get direct numbers for this of the order of 5 megawatts per meter squared per Kelvin. These are consistent with other kind of more indirect measurements of these types of thermal transport processes. And it really is quite an amazingly low number for the conductance, or a high number for the resistivity. Essentially, the effective conductance across this 2D layer is essentially, this kind of atomic junction is comparable to what you would get from 300 nanometers of like a typical glass, which is already known as a very poor thermal conductor. So these are the origins of why energy dissipation is such an important issue for these types of systems. Okay, I'll just briefly mention that we've done other measurements kind of probing these types of TBCs using X-ray scattering in the monolayer. We can also do this by, for example, probing the relaxation of the energy as the system cools into the substrate. And the numbers one gets for these types of resistances are all essentially consistent to first order. Okay, so now here was the kind of first kind of big surprise in these experiments. We said, all right, now let's repeat this experiment again, but now we remove this top metallic layer and we directly electronically excite the WSE2. So we're coming in with a 1.65 EV excitation. This is above the gap, essentially resonant with the first exciton peak for WSE2. It's below the absorption edge for WS2. So all of the energy is selectively deposited in this top layer of this atomic junction. And then the question is, how is energy shared, again, between these two structures? Okay, and so now here are the experimental results. Again, change in the temperature for each layer as a function of time, but now the time axis is increasing on kind of 1 picosecond timescales. So rather than hundreds of picoseconds, you can see the two layers essentially heat up almost concurrently, essentially synchronously within of order 1 picosecond. Okay, and so this is saying that essentially, even though we've deposited all of the energy initially into the WSE2, okay, essentially the energy is shared between the two layers and they largely equilibrate within a couple of picoseconds. Okay, so what's the mechanism and how do we understand what's going on here? So the first thing you can say is that this response is not directly kind of phonon mediated. It's not essentially associated with thermal transport, right? Of course, in the first step, we create a very hot top layer. And so you could ask, well, maybe energy is just directly shared, using the thermal boundary conductance, essentially, that we just measured. But what you can show is that essentially, using the TBC that we extracted in the first part of these measurements, this would have given rise to a very large time delay in the heating of the underlying layer, many tens of picoseconds. So you would need an abnormally large thermal boundary conductance to essentially enable kind of energy sharing through this perspective. So it's got to be a more complex electronic kind of mediated, charge transfer mediated kind of process. So what's the mechanism for underlying this? And so to figure this out, we started working closely with Felipe de Jarnada, Jonah Haber, a number of others at Berkeley and at Stanford to kind of work out a first order model for what's actually going on here. And the picture that emerges, I'm not going to have time to in detail describe all of this, but the picture that emerges from this process is that this kind of concurrent heating is caused by essentially excitation into a hybridized electronic state. So here's the kind of cartoon picture of the band structure, the layer projected band structure. So red here corresponds to contributions from the WSE2, blue from the WS2. So in the initial kind of step one excitation process, we're populating the K valley of the WSE2, this kind of region right around here. Okay, and there's essentially negligible hybridization between the K valley of the WS2. So this is again saying that there's no kind of mechanism for kind of direct coupling between these two structures. However, what you do see when you compute these band structures is that there's another part of the band structure. This is called the lambda valley, or also sometimes called the Q valley of the structure. And this structure is actually hybridized. This kind of whitish, kind of grayish kind of color here is indicating that this has significant contributions from both WS2 and WSE2. So the kind of proposed hypothesis here is that there is initially very fast coupling to this kind of lambda valley. This hybridized state then can couple directly through the emission of phonons into both layers simultaneously and couple directly into the top semiconductor and the bottom semiconductor. Okay, so concurrent heating arises from phonon bidirectional emission in both layers during the electronic transfer step. And here are some kind of calculations which kind of summarize the arguments for why this seems to be reasonable. In this kind of, these are essentially momentum resolved electron phonon coupling kind of calculations. So we initially excite at the K valley of WSE2. And what these color plots are essentially encoding is, essentially the rate for coupling to various points in momentum space, essentially. And these kind of bright regions here, these correspond to kind of 3 of the 6 allowed lambda values of the structure. So this first calculation is essentially showing that there is direct fast coupling to this kind of lambda valley, this hybridized kind of structure. You can also, through these calculations, essentially decompose the contributions of which phonons are essentially contributing. And interestingly enough, the calculations indicate that it's the acoustic modes that actually play the dominant role in enabling this coupling. Normally, when you think about hot carrier relaxation in semiconductors, it's almost always thought of as the optical modes are playing the kind of key role in mediating hot carrier relaxation. But here it looks like it's the acoustic modes that are contributing most strongly to the coupling to this kind of lambda valley here. And you can also see from these calculations that there's really negligible direct coupling to the K value of WS2. So that's the first step. And then the second step is the coupling from this hybridized lambda valley into both structures. So essentially giving rise to this kind of bidirectional phonon emission. And again, one can kind of compute these kind of full momentum resolved electron phonon coupling processes and directly and which essentially supports this kind of proposed model. Okay, so let me say a couple of comments about all of this and also some ideas and thoughts on the future. The first maybe thing I should say is that as you may have noticed, in our experiments, all I showed were measurements of the kind of overall temperature of the structure, right? And so we did not have essentially direct momentum resolved measurements of which phonons were essentially playing a role. We were measuring a Debye-Waller factor, essentially, which essentially sums over all phonon modes in the system. And so these a key argument, a key direction going forward is to essentially extend these approaches to go beyond just measuring the intensities of Bragg peaks and really try to probe the diffuse scattering itself. Here in a diffuse scattering measurement where you probe off of a Bragg peak, you have momentum specificity, and you can essentially define a particular momentum transfer and directly probe the response of, say, a phonon associated with that particular momentum. So these are kind of key arguments, key ways in which one needs to push going forward. I will mention there's already been some kind of very important work, and this is experiments from Brad Silwick's group, for example, in monolayer MOS2, I believe, essentially probing the kind of buildup of the kind of low energy acoustic modes. So the black areas are kind of Debye-Waller-like response, but you can see the Bragg peaks are broadening outward as well, giving rise to excitation into into the low energy acoustic modes that are kind of mediating the relaxation processes in these systems. And we've been thinking about this from a very kind of broad perspective, with respect to the hybrid perovskites, thinking about inelastic scattering processes, diffuse scattering processes to kind of get information on this kind of which phonon information, which really underlies and is going to be key going forward in terms of connecting to that theory. The bottom, let me just play this animation one more time. The bottom here are sort of just one more example of the kind of power and the kind of amount of information that is really encoded in these types of diffuse scattering types of measurements. So let me just briefly mention it, and then I'll play the animation one more time. So in these experiments, I already mentioned at the beginning of this talk, for example, that in these 2D layers, you have all kinds of heterogeneous types of distortions, local displacement fields, varying on the nanometer length scale, mediated by interlayer interactions in these systems. So in this kind of simple models here, this is just a simple kind of Python experiment where you take kind of a 2D layer and you think about, all right, well, imagine that I have kind of two local distortions dynamically expanding, for example. And so let me actually try to play it. So here these are kind of like two nucleation events or two kind of local defects coupling to their environment as an expanding acoustic strain field. And this strain field is then directly related, essentially the Fourier transform of the structure is what you measure when you do a diffraction experiment. And you can see the kind of amazing complexity of the diffraction pattern. These are the actual Bragg points in the structure. And then everything else here is essentially information, encoding information about the heterogeneity. When you have two distortion fields, you get interference effects, as kind of shown here on the right, and so on. So there's an amazing amount of information. There's never been an experiment, as far as I know, that has really, had the signal to noise to directly access all of this information in the diffuse scattering. There may be, a few kind of heroic kind of first order experiments pushing in this direction. But this is, I think, really a key direction going forward in terms of visualizing this kind of dynamic heterogeneity. And then more broadly, I think these new measurements define kind of a new mechanism for, a new understanding of how energy is shared across atomic junctions in van der Waals systems. And with that, I will conclude, and I'm happy to take any questions. Thank you.
Great, thank you very much, Aaron. A very interesting presentation. Some of those movies are really something to stare at too. So do we have questions for Aaron? And we're getting a little bit into our break period, but fortunately we have some time here also. So with regard to the what you say is the hybridized state, when you have the interlayer system, that does not show up optically, is that right? Because it's an indirect type of transition, or it looked like it's the electron density of states also. So it's both indirect and only in
That's right. Yeah, I'm not aware of any optical measurement which is directly sensitive to that type of intermediate state. Yeah, that's correct. That's part of the challenge of trying to unravel these things.
Okay. So that also seems like it would, or one of the things I thought I'd say also in future directions are with other TMD systems or other, very thin 2D structures. This might be a pretty universal thing, or if it's critical that you have this hybridized state, it could be unique to that system also.
Yeah, that's an important question. Yeah, I guess I don't know to first order. My guess would be that this is not something that is very specific to the particular material class that we chose. But yeah, we'd have to do some more measurements to really get at that.
Mm-hmm. I mean, it also makes me think of things like emission of virtual phonons or some kind of exchange that might be where you don't really think of population transfer until you end up with a real transition that you can go to. So there may be kind of complex descriptions of it also. So it's making me think of people like Philippe Guillotinet, where he'll think of how intraband cooling occurs via mid-infrared type of phonons, but where you can essentially have the equivalent of FRET processes in the mid-infrared that that might be ways to transport energy still in these types of manners. So not a virtual phonon, but virtual photons in the mid-infrared wavelength. Any other questions for Professor Lindenberg? Okay, great. Well, thank you very much for the. Oh, sorry, I think you're muted, Aaron.
Sorry, my connection dropped out, so I didn't hear the last maybe 30 seconds. Yeah.
Oh, okay. No worries. Do other folks have questions? Okay, no, remarkable presentations this morning, and thanks to all the morning presenters. We have a little bit of break period here where people are free to run about for a little bit as they'd like, or to stay connected here and chat as folks might want to. So we resume presentations at 11 a.m. Central Time. So
Rich, is it okay? Oh, sorry.
No, go ahead. Go down, please.
Is it okay if I test my share screen and all that?
Yeah, no, you bet.
Um,
Aaron, what's your experience so far with, oh, sorry, you dropped off for a second for the break. Yeah, if you go ahead and click share screen, it's the green one on the bottom. Yep. Yep, that looks good.
Is it moving? And you see my pointer, like just the
Yeah, we can
mouse?
see your cursor and it's the right mode of presentation.
Sorry, Tim. I know you've heard this 1,000 times.
It gets better every time.
All right, well,